So, good afternoon, everyone. So today we are going to continue with the arch models, and today I'm going to illustrate how this whole arch fitting is done. You may see I'm in a different format because today I'm in the department taking this lecture. Otherwise, I used to take it from the home. Anyway, so what is that the steps involved in this whole business? So I'll just try to write them. Now let's so arch fitting. So I'll write step by step. So what you have is you have the data. I'll just call it as RT. Of course, we used to call by YT. These are the returns or any time series. Okay, so the step by step we will write this. The first step is that I would like to fit the mean, in the sense that so I'll assume that you have the model RT equal to mu t plus epsilon t. So I want to fit an appropriate model for mu t, which is equal to expected value of RT given ft. Yeah, so assuming that you have up to t minus 1, RT given ft minus 1. Okay, and that is for the prediction. If you are actually considering for this, that is a conditional mean, you can say, sorry, you can still say that this. Now, what is that we wanted? This fitting, oh sorry, I think it is t minus 1, I'm sorry. So what is that we wanted here? I want to fit this and then try to get, like, for example, you can have an AR, you can have ARMA, so you can have a moving average, you can have a ARMA, you can have a ARIMA, you can have a seasonal ARIMA. So this could be the model that you are fitting for the RT. And then the specification of this according to this, and that we have already learned how to go about this. And once you fit this, I would say that you have a mu t hat. Once fitted, the mean we have mu t hat. Okay, so for example, it's something like phi naught plus phi 1 RT minus 1. It could be just like that, and once fitted means you have these values. Okay, or some different way, I mean, like any different way that we already learned how to fit the main model. Then the next step here, so step 2 is at the end of this, if you want to make sure the fit, so we'll have this involves, once you identifying the model. So what are the steps involved here? The steps involved here is oh no, sorry, actually there is some problem. I think whatever I have written yesterday, it's still remaining. I think I'll just but then I have this thing actually, so I want to continue here. Okay, Okay, so let's be here. So what we have here, once we fitted this, we generally use the model identification, estimation, fitting, and diagnostics. Which basically residual analysis. So in this process, what we will do is basically, so RT minus this mu t hat, which is a kind of epsilon t hat, and then you get the ACF PACF of epsilon t hat, and found within the range and all other residual analysis satisfactorily done. We stop the procedure. So the procedure will be stopped at this point. The whole procedure will be stopped at this point, and what you will have here, once I have this, actually, this was, okay, so this, and then what we do is that at this point of time we say that, okay, the model fitting is done, you have an appropriate model. Okay, so our basic what to do next is, like, we may forecast. So we may do forecasting for RT. Okay, so what is happening at this point of time? Not getting good forecast. So one way to address the problem is perhaps the model finalized is not good. May revise and do it again, everything again. Okay, now this is actually we may do all these things again, but the problem is not that. What is actually happening is that even if you do it again, I am not getting very good result at this point of time also. So then I start suspecting there is something wrong, and as I told you, if your original time series having a lot of up and down movement on very continuously over the time periods, it basically indicate that there is a possibility of volatility or conditional variation. So what we have to do at this point of time is arch effect. Test this arch effect. So how this can be tested? So plot ACF PACF of this, or and I would say and this. Now also do link box and Lagrangian multiplier tests for this, which we have discussed in the last class. Now if both indicates that there is an arch effect, we have to go for arch modeling. Okay, so how will you go for the arch modeling? That is what the point that we have here. So one of the ways is like what you can do. By the way, here after onwards, I will remove that. I will not use that cap. I assume that that cap with cap is same as uh, for notational convenience. Assume that with cap is same as whatever without cap. Okay, so uh, we treat which is equal to as the data. So I have the data, and what I want is basically I want to have a model. So first thing that I do in this context is when I say the Lagrangian multiplier test, that also gives me, you are testing like this, alpha naught plus alpha 1 epsilon t minus 1 square plus etc. alpha m epsilon t minus m square, and then you are now trying to see whether alpha 1 equal to 0, alpha m equal to 0 versus uh, at least one of them. So this implies, and if you reject this null hypothesis, so here reject h naught implies there is an arch effect. Okay, so once you have this arch effect, of course this can be identified by this ACF PACF of absolute and squares also, because that also gives you an indication. So this is also equally useful to decide that ACF PACF. So this and this test. Now once you have this, so the next step is basically is actually to come up with the model. So some hint you are going to get by this testing, saying that for example we can look at the PACF of, so to start, because every time series what happens, if you want to do something you need to have a model to start with. Of course later we can polish that model. So to start with, to know which arch model, arch M, is to be used, that means value of M. We use the PACF of epsilon t hat square. So what we do is that using we know that we can determine the order of an AR structure. So you see here you have kind of, this is a AR kind of structure for the epsilon t square. So now you see the similar properties hold good here. So I can decide based on that how many, like alpha 1, alpha 2, alpha 3. So alpha 3 is the highest value which is significant. So I will consider order of 3, arch of 3. Alpha 2 is the highest value significant, afterwards it is not significant. See, you can have sometime insignificant in between also. See, for example, alpha 1, alpha 2 may not be significant, but alpha 3 may be significant. Still, you have to go for an order of 3. And then, in the process, you can eliminate the other two later. Okay, we can actually modify the model later. But generally, go for the highest coefficient, which is significant in this context. So that is what we do in this whole exercise. Okay. So this can be decided by the PACF, looking at the PACF as well as the Lagrangian multiplier or link box test. So we can do it by looking at that. That's what we do here. Okay. So once M is decided, for example, m equal to 2. Fit the model arch 2. So what is the arch 2 model? It is basically epsilon t is equal to sigma t zt. Z is IID 0 1, okay, and sigma t square is alpha naught plus alpha 1 epsilon t minus 1 square plus alpha 2 epsilon t minus 2 square. So I'm going to fit this model, and this is done by in R what is called as GARCH. There is a soft library, and once you use this, you can actually fit them in one command. Once you have this particular one, what we have is basically so we take, so basically you are trying to, now in the process when these are parameters are estimated, if suppose this turned out to be insignificant or this turns out to be insignificant, we can rework on the model with m equal to 1. Okay, so that's where you have this particular facility. Now once you have this, so what is that, yeah, once this is done, so we have fixed that, we have fitted the model, so you have this entire thing. And now if you want to do the residual analysis of this fit, that is we want to carry out the residual analysis of this fit, of this arch fit, how it is done. So that is done. So once you fit this, you will be knowing sigma t square cap. Put a cap, which means that you estimate these things. These are observations, so this is known. So what I will do is that I'll consider zt. Zt is something which is not observable, but I'll get zt hat by using epsilon t sigma t cap because of this thing. Now zt, we have some assumptions. The assumption is they are IID 0 1. Okay, so what I will do, I'll see whether these assumptions are really true for the zt hat. How will you do that? Again, look at the ACF, PACF of this. Also plot residual analysis, because I wanted to know whether this is concentrated around 0 because it has mean 0. I wanted to know the variances are not very large because its variance is 1. So this variance should not be very large. Also this ACF, PACF tells me that now they are uncorrelated or independent, because I assume that they are independent. So that assumption also we are going to have it from here. So I am going to do this exercise of zt hat. Now just to make sure that what you have done is correct, it is advisable to go for ACF, PACF of this also. And if all these things are satisfied, you have done. So you have done with your job, and we have the volatility equation available with us. We can do the volatility forecasting, which we have discussed yesterday. So we can have the volatility sigma t square hat, t plus k square hat can be forecasted, right? You can see the formula. We have derived the formula yesterday. So this is the step-by-step procedure that we follow. Now I'll just explain this with this particular data set. So you have this data which is the return from Intel series, and this is the series. You can clearly see that there is some kind of a volatility is happening here, 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 because there are a lot of variation is happening, too much of variation. Okay, this is from 73 to 2008. Now if you look at the ACF, now what happens that I just want to tell you one more thing. Sometimes, you know, this fitting node, sometimes we can directly consider RT as epsilon t when it is done, because when the given series itself behave like like a white noise, no need of fitting mu t. So the given series itself you can take it as epsilon t. But sometimes you may have to do, otherwise if this is not the case, you may have to do AR, MA, ARMA, etc. for the mean, and then the mean has to be estimated and it has to be subtracted, right? So sometimes that depends on the data. So here, for example, in this particular case, if you look at in this case, the four graphs are given. This is ACF. So the ACF of log return. Log return is log PT upon PT minus 1. That is what log return. So you can see that the log return itself is like a white noise because nothing is going outside. So it essentially means that you don't have to really do a mean fitting for this particular data. Okay, sorry. And this is ACF of squared return. Now you see ACF of the returns are within this limit, but ACF of square return are not within the limit, which means that the variance of the returns are changing across the time. That's what sigma t square is changing. So this gives an indication that the variances are changing, right? Now the same case, if you look at C, is the absolute of log return. So you can see that the same phenomena happens for absolute also, where it is not happening for the returns as such. So square and absolute shows that the correlations are running or changing across time, which implies that there is a need for arch modeling. Okay. And the last picture is PACF, because PACF basically help us. This is PACF of squares. So this tells me 1, 2, 3 are significant. I am ignoring this because if I consider this, the order will be very high. Actually, we don't have to go so much of the far away. So generally what we do, we start with a model arch 3 in this case. So that's what PACF of squared log return. Now you have to consider the square of the returns if the returns behaves like a white noise. If the return doesn't behave like a white noise, you take the series, fit the mean, then subtract the mean from that, and then consider the residual, and then for that residual you take the squares and then fit this ACF, PACF of that, compute the ACF, PACF of that to see whether the, of course, PACF is the one which we are interested because we have a AR type structure. So in this example, I will be going for a arch 3 to start with. Okay. Let's look at, so this is what I said in the beginning. Now, so this is the R command. This is a specific command for only those statistical tests, because this is graphically, I have identified that there is an arch effect. The same thing can be identified by a Limbox test as well as Lagrange multiplier test. So this is Limbox. So this is for the data, and then this is for the Limbox test, and this is basically for the square of that. So you are now trying to see the square. This is for the actual observation, the returns. This is for the squares. See this INTC actually stand log of this. Okay, so that's what log returns is already computed, INTC. So this is log returns, and this is log return square. Okay, so now you see that this p-value, this is not significant, whereas this this p-value is significant. So the same phenomena that this is not significant, whereas this is significant. Okay, that's what we are seeing by this. So now, as I was telling, because I am going for a model order 3, so my model will be the sample ACF square return clearly indicate conditional heteroscedasticity. The Limbo's test also indicate the same. PACF indicate R3 is an effect. So this is the model. But I am not doing this one in this case because directly your returns, log return itself behaving like a epsilon t. So no need of this mu t fitting. But we need to consider these two. So the arch means this whole stuff together. That's what the arch. This is arch 3. Now the next step is, so here that mu t thing is not there. So RT itself is epsilon t. So you have this is observable, and then you have this equation. So we need to now go for the estimation of this alpha naught, alpha 1, alpha 2, alpha 3. That's what we are estimating. And we have some restrictions like alpha naught should be always greater than 0. This should be greater than or all equal to 0. So you fit them, the R command for this. As I told you, the GARCH fit is the package. GARCH fit is the command, and FGARCH is the package. So you see the library, you may have to, if it is not there, you have to load that. You know everything. So I don't have to tell anything about this. This is how the data looks like. This is like a log return. So in C, and then I'm putting using the GARCH fit command. So GARCH fit, and then GARCH 30 is essentially meaning a arch. Now this I'm jumping one step ahead because GARCH is not introduced to you, but then you once I introduce, then you will come to know. It's like ARMA and AR and MA. So in an ARMA, if I take the moving average coefficient as 0 or moving average order as 0, it is a AR model. So exactly the same thing. Here if I have taken this as 0, so this is arch 3, and then this trace f is to control the output. Okay, so you can experiment it without that and with that and see that what kind of outputs are being controlled. So now here you can see this parameter estimated. So in this notation, this mu, so here what happened, this mu t is taken as mu because there is a minimum return that is available. So there is an average which is estimated, and that is estimated here. So which is significant at 5% level. And then there is a omega. This omega actually stand for this alpha naught. Okay, because this book, these people use this notation. So omega, and then alpha 1, alpha 2, alpha 3, which is here alpha 1, alpha 2, alpha 3. So this is so we see that this is only alpha 1 is significant, these two are not significant. So actually it is enough to consider an arch 1 model. Okay, so that is what we do in the next step. So here I am going to do it that thing again and consider a arch 1 model, and then you can see the output. So here this is what the mu, this is omega, and this is the alpha 1. So I don't have this alpha 2, alpha 3 because they were turned out to be insignificant here, not significant. So I go for a arch 1 model, and then now that you can see the arch fitting is done, you can actually go for what is the likelihood value, what is the normality test, the link box, because we have assumed ZT this to be normal. You see, in this model I have assumed that this ZT is normal. So once you estimate this arch 1, so this is not there, you are estimating alpha naught and alpha 1, so sigma t square you got. You divide epsilon t by sigma t, and this zt, you subject this to normality test because I am assuming that zt is normal. So that is what being done here. You can see that the normality test is done. Link box test is at various order, like I am considering 10 correlation square, 20 link box test. This is for the residual, this is for the residual square. Okay, and the Lagrangian multiplier test for the residual. So you can see that these tests, which of them are rejected, which of them are not rejected, you can just see that. So the R, it is insignificant, whereas R square is significant. So you can see that there is an arch effect. And whatever the model, this is of course standardized residual test. This is so you can see that this is R square, and then you have the information criteria, which basically if you have 2-3 competing model, of course information criteria useful when you have 2-3 competing model. So I can get the corresponding information criteria, you can plot the results. So this is, now if you look at the residual and residual ACF, PACF, so you can see that this is the standardized residual. Standardized residual means epsilon t divided by sigma t hat. So that is what ZT has. So you can see that they are not varying too much. And the ACF, PACF of that is lying within this line, except this one. One or two, I mean, can go up, I mean, because this is a sample thing, but majority or most of them lie within this, which means that the model that you have chosen, Arch1, is giving a good fit to this data. Okay, so the expected monthly, now what is that conclusion that you can get? Expected monthly log return of Intel stock is about 1.31%, which is quite good. Where did you get that? 1.31%, it is here. So you have, this is mu. So you can see that this is the expected return, expectation of RT, because expectation of this is 0. So I told you there is a mu here. So that is what that 1.31. So on an average, you get about 1.31%, quite good. Now, alpha 1 cubed, it is about 0.3750 cube, which is less. This because alpha 1 is estimated by this quantity. Where is that? Sorry. Here 3750. So alpha 1 is estimated by that, and then so we have some condition, unconditional fourth moment of the monthly log return of Intel stock exists, and the unconditional standard deviation is standard deviation is alpha naught upon 1 minus alpha 1, and that is variance. Square root of that will be standard deviation, so which is about 0.1327. So ARCH1 model can be used to predict the monthly volatility of Intel stock. Now, somebody asks you how much variation will be there in this the price of the stocks. So we can say the sigma t square can be predicted even in advance. So that's what the volatility prediction. Now, instead of the normal, if you can in the GARCH fit command, you can bring, if you don't write anything, it will be normal. If you write conditional dot distribution is student t, so this is basically STD stands for students t, so you can use a students t distribution, etc. So the ARCH model assume that the positive, and now what these are some of the drawbacks of that. So for example, your ARCH model is basically, sorry, the arch model is basically, if you look at this, epsilon t is equal to sigma t zt, and sigma t square is alpha naught plus alpha 1 epsilon t minus 1 square. This is what we have actually tried to take it. Ooh. So what happens in this case is this particular model, epsilon t, you get this kind of a model. Okay, this is what your arch one. Now what I am trying to say in this, you see this one. So irrespective of epsilon t minus 1 less than 0, epsilon t minus 1 greater than 0, the today's variance is going to actually have the same value irrespective of whether this is negative or positive. That means in yesterday's, this error happened by an increasing in the price or a decrease in the price. That's not going to make an impact on. So this is one of the drawback. So this is called, you have symmetry in the model because positive or negative is going to give you the same variation here. That's not very true from a practical point of view, because if you start looking at the returns, you can see that the empirical side, you can see that the down movement, this I mentioned in the beginning, down movement will have more variations as compared to the up movement. The bear market and the bull market will have a different phenomena or different kind of variation or different kind of volatility, but that is not revealed in the arch setup. So this is what one thing that I would see. Just a minute. Hello. Okay, so I'm sorry. So this is what is happening in this whole context, and then what you have is okay. Let us go back to the. So arch model assumes that positive and negative shock has the same effect on volatility. In practice, the price of a financial asset is respond differently to positive and negative shock. Okay, the arch model is rather restrictive. For instance, alpha 1 square of arch model must be in the range 0 to 1 by 3 if the series has finite fourth moment. This we have seen the derivation yesterday. If the fourth moment further restrict the range of variation of alpha 1. So 0 to 1 by 3. If you don't have any moment restriction, it can go up to 0 to 1. But then the more moments I demand, it starts further decreasing the range of variation of this coefficient. I am now talking about arch 1. Okay, then I can talk about alpha 1. Okay, but if I talk about alpha m, then it is very difficult to make these kind of statements because there are more number of variables. So the constraint become complicated for higher order arch model. That's what I mentioned here. The arch model does not provide any new insight to the understanding of the source of variation, because this doesn't tell me what was the reason for variation. It just tells me that there is something is varying, but it's not clear what is the reason for the variation. So the model, and not only that, the models are likely to over predict the volatility because they respond slowly, isolated. So the sense that what is happening is that it keep on adding, so the clustering effect is there. So most of the time when you estimate the volatility, it actually try to over predict the volatility. So this is another drawback. So these are some of the drawbacks of the arch models. Okay, I think that's the end of it. Thank you.